Well, here we are again. This is Mr. McAllen, and I am talking to you about power series. We started out with the last lesson where we defined an infinite series. We defined a series that diverges and converges. We showed examples of such. We showed how geometric series can converge under certain circumstances. And now what we're going to do is we're going to start out and we're going to talk about the geometric series, as I wrote before, where we had written down the general term and I'm just writing out what the series is here. And what we can do is we can actually, we know what this is going to, if R is between 1 and -1, we know what this is going to sum up into. In fact, I'm going to say that my first value A is just equal to 1. And my R value, I'm going to call that X. So it looks like a polynomial. And this is ingenious, whoever came up with this, because we have a nice polynomial which looks like this. It's 1 plus x squared plus x cubed plus ... It goes up to x to the n, and that's all going to sum up to 1 over 1 minus x. And this comes from the geometric, I guess, discrete math, when we did arithmetic and geometric series, where we said that if you have a geometric series, and as long as r is between 1 and -1, the sum of all the infinite terms would be equal to the a value over 1 minus the r, as long as r was less than 1. Well, in this case, r is between 1 and -1. But it's ingenious because if you look, this is a string of polynomials. Or it's a string of a polynomial. And we're saying that that's equal to a function. And this is basically a starting point for us in BC Calculus, where we want to understand how we can model a function with a polynomial string. So here's what we're going to do. We're going to use our graphing calculator to kind of show how this works. And so what I'm going to do is I'm going to program into the calculator y1 equals 1 over 1 minus x, and into y2 I'm going to program in the function 1, and then I'm going to add to it x, and then add to it x squared, and add to it x cubed. And each time I change it, you're going to see how much better this polynomial here fits our function. So let me just do that now. I'm going to pause the camera while I get the calculator rolling. Okay, folks, what I have here is I've programmed in 1 over 1 minus x. And that's our formula for the function we want to plot. When we look back at the function, that's what I said I would put into y1. Now, when I go back to the graphing calculator, I'm going to program in for y2. I'm going to start by just putting in the function 1, because that's the start of our polynomial string. When I graph that, you're going to see that I only match at a point. I'm going to change that, and I'm going to add the first term of the geometric series, which is, the second term, which is plus x. And when I graph that, you're going to see I now match at a point of tangency. And now I'm going to put in my next term. And actually, if you go back to AB Calculus, the first semester of Calc, what we have here, the first two terms, basically represents a linearization at the point x equals 0. And we would have worked with that in AB as far as doing a tangent line approximation. Well, now we're going to make it better. We're going to add a third term, which will be x squared. So when I put that in, you'll see that we have a little bit better of a fit. As you can see here, the function comes down and it tries to approximate the hyperbola a little bit better. Let's add one more term. And as you can see, the big thing to realize here is as we add on more and more terms, our fit gets better. So let's just do plus x to the third power. And when I graph that, you'll see that our fit gets even better. So you have to admit that our fit is getting better and better, but if you notice, it's only happening in between (1) and (-1). And this should make sense because the geometric series only converges between 1 and (-1). So as you can see here, we've got the polynomial breaking away in this region, and it's over here it's okay, but on this portion here it's breaking away, and we really don't have a tight fit, but we definitely don't converge to the hyperbola outside of 1 and (-1). So the key points here is that our polynomial, which will be 1 plus x squared plus x cubed plus, and I can keep on going, so that will converge to 1 over 1 minus x as long as I keep x between 1 and (-1). That's the criteria for convergence for this geometric series. Well, here's another thing that we can do. Once we have this geometric series working, you can do different things to it. For example, if you were to take the derivative of this side, the derivative of this would be (-1 over 1 minus x squared. Actually, let me check that. We have 1 minus x to the negative first power, so when we take the derivative of that, we have (-1 in front, 1 minus x to the (-2), and because of the chain rule, we multiply it by (-1), so our derivative is actually 1 over 1 minus x. Quantity squared, that will equal, if we take the derivative of that term, that should equal the derivative of this geometric series, which would be 0 plus the derivative of this term is 1 plus 2x plus 3x squared plus ... and this would end up being nx to the n minus 1 would be our general term. So, and what this shows us is that not only can you take a function that you know converges because of if you take the derivative of one side, then the derivative of the other side, they have to equal. As long as the series you're operating in the interval of convergence, this will hold true. So just because we had a function we took the derivative, the interval convergence is still between 1 and (-1. But taking the derivative doesn't change that. It in fact gives us another function we can use. If we can take the derivative, we can also take the integral. So if we start out with our geometric series again, and we integrate this function, then this would be the if we integrate this side, then we would integrate this side, and we do term by term integration over here. So this would be x plus x squared over 2 plus x cubed over 3 plus x to the fourth over 4 ... This would be x to the n plus 1 over n plus 1. This would be the polynomial series that would approximate the negative natural log of the absolute value of 1 minus x. So that's pretty handy. Another thing we can do with this is we can take our original function and we can, if you just have this to be 1 over 1 minus x, you can consider what would be 1 over 1 plus x, because what you really do is you plug in for x negative x. Pretty tricky. So what we do is everywhere there's seen x over here, we plug in negative x. So we have 1 plus negative x plus negative x squared plus negative x cubed plus negative x to the fourth, dot dot dot, and what we end up having is we have an alternation of signs. And for the general term, we would have this equal to the summation of negative 1 to the n power x to the n, and again the convergence criteria for this geometric series would be x has got to be less than the absolute value of x has got to be less than 1. So hopefully this short lesson has helped us explain a geometric series as a polynomial, some spin-offs by doing different things to the geometric series, and what the convergence criteria would be. In the next lesson, I plan on going into more detail about how we actually construct series functions, as in a Taylor series or a Maclaurin series. So I hope this helps, and I look forward to talking to you again.